In this video, I want to talk a little bit about non-software engineering usages of Big O. And really what I mean by that is mathematical usages. So here I'm going to talk a little bit about sort of the direct usage of it. So you can actually have Big O as part of expressions. So for us, we usually do things like having f of n equal O of n or something like that, right? Basically say that this particular function has a Big O bound of this. That's fine, right? That's typically what you see in software. But it's actually the case that you can have Big O as parts of expressions. So over here I have 4n squared plus O of n, right? That's one whole expression. What that is actually indicating is that I have an expression, right, whose value is 4n to the n squared plus O of n. O of n isn't really a value. We've been using it as an upper bound, right? But what we will actually think about is, or what mathematicians and physicists think of it as, is an imprecise value. So O of n is basically some quantity that varies as a constant of n. So I'm not actually looking at a single value, right? That expression there, 4n squared plus O of n, is not just one value. It's a family of values that all kind of vary because of that flexibility offered by that Big O term that's being added in. Note that that expression doesn't vary in value all that much because that Big O is just on n, right? If it was on n squared, it would vary, as a square. If it was n cubed, it would vary as a cube. Here it's just kind of a linear variation. The point is I'm adding a little bit of flexibility. So this is completely fair game. If you were to take maybe an advanced course on algorithm analysis, you would actually spend many weeks learning the algebra to manipulate these. It's not typical algebra. I'll have a little example on the next slide. It's a little bit different, but you can actually do all sorts of operations with these little Big O terms, and they'll kind of change around, right? They'll sometimes disappear, sometimes they'll appear from nothing. It's again just a way to represent inexact quality. So as an example of some of the manipulation we might want to try to do, right? Because it is, a term in an algebraic expression. Let's take a look at these three little bullet points here, right? So we have to be a little bit careful, right? If we want to all of a sudden start thinking in this more general mathematical usage of Big O. Because what happens is we get stuff like this. We have down here 1 equal O of n. From our previous discussions, that should be fine, right? The function, f of n equal 1, that's obviously bound by O of n, right? O of n is linear growth, right? So for sure, I can imagine that that'll be, over that constant value. It's easy, right? Linear is always going to go faster than a constant. So that's fine. So 1 equal Big O of n, of 1. Then we have down there 2 equal Big O of n as well. And this again is fine, right? So obviously linear can bound constant. So both these things here are true, right? And that's just based on the discussion we've had previously on how we look at growth functions and we derive a Big O expression for it. But the problem is, right, when we starting to think about Big O in a more general way, is that we then think to ourselves, oh, I can do that and that and that. Therefore, what I could do is I could have 1 equal Big O of n equal 2, right? And then I could have 1 equal 2. Clearly, somewhere, something broke. Where it broke is that idea that Big O is an inexact value, right? When I have a term in an expression that has a Big O associated with it, that is an inexact value. In fact, right, in terms of the math behind the scenes, it's a set. So Big O of n is a set that has basically every multiple of n union together, right? So there's many different values in there. So it's actually incorrect for us to say things like 1 equal O of n. Now, that is the typical syntax, right? For software developers, when you read pretty much anything, when you go and you look at code, right, the only thing you always see is the equal sign. But that is wrong. A Big O expression, right, or a Big O term is actually a set. And so if we wanted to be more precise, we would say it's something like what we have at the bottom, which is 1 is a member of O of n, right? So that is a true statement. The set of all the things that vary like n does include the number 1 and number 2 and all these other kind of low constant values. Well, it includes a ton of stuff, but it all varies kind of according to n. And there are many different choices, right? There are many other things that n bounds, not just 1 or not just 2. Because of this, there's really some directionality behind the scenes. That equal sign is not fair because equal, well, basically, A equal B is supposed to be the same thing as B equal A. That's not the true for Big O because it really is a set. And when we talk about the equality, it's in terms of set operation. Now, if you try to work this out on paper, you'll see that if we basically change, right, to using that subset notation, right, you'll see that we no longer have the issue of 1 equal 2, right? That doesn't emerge because the directionality kind of goes in a different way. So keep that in mind, right? Big O, right, can occur in expressions. Mathematicians use it, physicists use it. And you can do algebra on it, but the rules are just a little bit different.